great to have you here. Abdullah Khalid from QWorld. Would you like to give a long introduction to yourself? Because you will give 4 sessions the upcoming weeks. It will be great to know more about you.
Absolutely. Thank you, Marlo, for inviting me to the session. I'm glad that there's so many people here. It's great that so many people are interested in quantum error correction. So, an introduction to myself: I'm a physicist, and my expertise in quantum computing. So I did my PhD like a few years ago, and then I was a professor at the university for a few years. It was a lot of fun time, but eventually I kind of decided that I wanted to experience the world in a different way. So now I work in the quantum industry. I think which a lot of you are also interested in. So if you have questions about that or anything like that, feel free to hit me up and ask me what your journey in this field could look like. Yeah, I think that's kind of a basic introduction to me.
Great. Any questions to Abdullah, everyone?
Yeah,
Daniel asks, is this the Abdullah who did the evaluations? On Canvas. Dawal, the answer is yes. This is the Abdullah who did the evaluations for many of the past quizzes.
Oh, yeah, I see. So just to be clear, I'm not like sitting there all day, 24 hours a day, just as soon as somebody submits an answer to their assignment, I'm quickly checking and submitting feedback. There's an automated process that does it. I wrote it, and the way technology sometimes works, I ended up like sending, I went lazy and I sent the feedback back under my own account. So
not lazy, clever. Yeah, great. Okay, if there are further questions, we will see it coming, and Abdullah will get ready for the first lecture on quantum error correction. And if you could also share a bit, Abdullah, what quizzes there will be and how to pass this module, that will be great.
Yeah, absolutely. I'll do that. So I can share my screen now, and let's see.
And Farda, the answer is yes. Abdullah will also be the one to evaluate the quantum error correction. Definitely
yes.
fun. Yeah.
Okay. So as you know, let's go here. Yeah. So as you know, that this is a sequence of 4 sessions, all conducted on the weekend, on Saturdays. So starting from today, the next 4 Saturdays, roughly around the same time. I think, Marlo, the times are slightly different, perhaps, for the sessions. I think that's how it appeared on my calendar. Or are we starting exactly at the same time?
You can all follow the Luma links that will be sent, and we will share an additional announcement about the time of the next weeks.
Okay, perfect. So so I think what we do is, like, the first step that you should all be doing is that you on your canvas, you go to modules, and then you go down, and then you here. So you click on this guy, and you open up the repository for the quantum error correction module, right? So you can, just as the same way you have done for the previous workshops, you clone it or download it in however you like, and you get it. You open it Jupyter on your computer. So I guess. So I think the first thing I should say before we go, what are the prerequisites for this workshop, right? So that's kind of important. So prerequisites. sorry, my handwriting is not the best. Okay, this is annoying. I don't know if you can see that. So prerequisites are you should at least have done QBronze in the QWorld domain, right? If you have done more workshops, that's better because then you have more maturity around these concepts. But the other thing you will probably require is that a good understanding of linear algebra. And by that, I mean more both abstractly and computationally. So you should be comfortable with thinking about vector spaces abstractly, thinking about vector subspaces abstractly, at least, and perhaps visualizing vectors, things like that. You should be good at, and you should also obviously be good at working with vectors and matrices by hand or on a computer. Yeah. So those are the prerequisites. And then once you enter here, you will probably just go to the contents. Okay. So you open the contents, and the first thing you want to do is you want to open the first notebook, which is about Stack. So Stack is this software library that I wrote particularly for this module, and it does other things as well, but that's how it started. I wanted a Python library to help with quantum correcting stuff. So basically what you're going to do is in your Jupyter, perhaps I can open it in Jupyter itself. So I have this thing open. Marlo, this is quite annoying. Do you see these on my screen, these admit notices?
But it is not seen by participants now, but you can ignore it.
Okay. Yeah. So I mean, I have the thing on my computer. So Stack. So basically, what you're going to do is you're going to run this command and will install Stack directly from GitHub, right? So it will just download and install. Stack basically allows you to work with quantum error correcting codes and there are some basically just testing of installations. So you can run a bunch of these cells just to make sure everything is working. So you'll see these nice pictures and whatnot, and we will by the end of this workshop be generating these circuits, not by hand, using algorithms. So you can see that there's a algorithm here that is being used to generate this circuit. Anyway, so the only introduction that I want to give to Stack is that we'll use the circuit library quite a lot. So there are really 3 commands here, or 2 or 3 different commands that we need. So once you import Stack, what you do is you can create circuits. And for this workshop, we will only be creating simple circuits in Stack. So you'll just say stack.circuit.simple, and then you put in the number of qubits that you have in your circuit, right? And then what you can do is you can add operations to your circuit by using the append command, right? So circ.append, and then you give the name of the gate, and then you apply which qubit it's acting on. Obviously, like we just need some basic gates, so H, X, Y, Z, etc. They're all built in. So CX, CZ, etc. So you put them in, and then what you can do is you can draw this circuit as well. So you get something like this. Let me look at this code and see if there are questions. I see the bunch of questions. Let me just go through this and then answer. The other thing you can do with the Stack circuits is that you can just run the simulate command. Okay. So what this does on the backend is just uses Qiskit to simulate a circuit like this. So basically what it tells you is that, hey, when you run the circuit, the output, the wave function at the end of the circuit will be, it will be the ket 00, which will have an amplitude 0.707, and ket 11, with amplitude 0.707, which I'm sure all of you recognize as 1 over square root of 2, right? So basically, this circuit is obviously creating the state 0, 0, 0 plus 1, 1 divided by square root of 2. The other thing you can do with stack is that you can sample things, the measurements in your circuit. So if you additionally add some measurements to your circuit, right? So the way you add measurements is just the M command, and I say that, hey, I want a measurement on both the 0th and the first qubit. Then I can sample it, and what we'll do is it will just sample it, and then you can see that the outcome is either you get 0, 0 or you get 1, 1, and these are all coming with roughly 50% probability, right, in this simple circuit. So stack is very simple to use. If I think there should not be a problem at the level that we are using it, but if they are, please do hit me up and ask me. I'm perhaps the documentation is not very good at the moment. I'll try to see if I can add some documentation so it's easier to work with it. Let me just look at Discord and see. Okay, so any recommended pre-reads for quantum interaction? I think so. I mean, Abdullah K has linked to this thing, which is the book that I'm writing. And basically what we are doing is we are working our way through this book. So the parts of the book I've written. So and the book has been written in a way that it's easier to, I think it's easier than a lot of other resources. I can give you a whole bunch of resources for quantum interaction, but I think they are all pitched at a higher level. So I think this is the easiest thing that you can get into. So oh, there was a simple command here, simple to integrate. So that not clear. So how can I say this? So there are more. So stack has this notion of circuits, which is quite complicated, and because it becomes useful later on for constructing more complicated quantum error correcting codes. But for our purposes, we want only simple circuits, so we use this command. And what it does is that it gives you an interface which is quite similar to other circuit libraries, so Circ or Qiskit or whatever, where you have something like this. If you try to create a circuit without this, you will see that these commands will not work on the circuit. You'll have to do some additional work, and we don't really want to do that additional work. So we'll just stick to simple circuits. Yeah. Okay. So I've hit all the questions for now. So let's go and let's go back to the contents, right? So in front of each of the things, so this is something you should do, right? Like as day 0 kind of thing, as prep for the thing. But then I've marked all the notebooks that you have to work through on every day of the workshop. So there are 4 work notebooks that you have to do on day 1. There's an additional thing, which is distance of the code notebook, which is optional. Don't have to do it. Day 2 is this stuff on quantum. So one of the things we'll do, and this is quite important, you'll notice that in QBronze we also did this, that to understand quantum, you can't just understand quantum on its own. You have to first understand the classical case, because you want to understand where quantum is different from classical and where the power of quantum comes in, right? That's what we're always doing. This quantum computing field, we are saying that quantum computers are better than classical in some way. And so whenever you study anything in this domain, you have to first see what classical can already do. So in this case, we'll spend a day on classical error correcting to really understand what things are here, and then we will go to quantum. Yeah, another advantage is that whatever we'll do in classical will be directly applied to the quantum error correcting case. Like we'll study what are called error correcting codes in the classical case, and then we will study analogs of those codes in the quantum case. So it's quite useful to see that and understand the simple case in the classical case, and then move on to the quantum cases. So day 2, there's a chapter 5 which is still in the draft pages, very small, and there are, I think, a few mistakes in there, critical mistakes here. So I would skip even reading it at this stage. It's still there, so I kept it there. And then you see that on day 3, you have these 4 notebooks, and then day 4, you have an additional 4 notebooks. So okay, so no more questions in on the Discord channel. So where we can go? Yeah. So I think we can start to think about what error correction is, right? So we are trying to solve a particular problem, which is that we are, let's see. So this is the kind of scenario that we have in that is for which we use error correction. So you have Alice somewhere, sitting somewhere, and you have Bob sitting somewhere very far away from each other. Okay. And Alice wants to send some information, some messages to Bob. You might think of Alice, picking up her phone and calling Bob, or sending a message through Discord, or sending getting on a Zoom call and sending a video feed through Zoom or something. And the problem is that whatever information she tries to send, there's a noisy channel in the between, right? So you can think that whatever she sends is getting corrupted in some way. Whatever information she sends, it gets corrupted. So what Bob receives is not exactly what Alice sent. How do Alice and Bob communicate? How do they reliably transmit information, through this noisy channel? And that is the kind of problems that quantum error correction tries to solve. So let's try to make this a little bit more discrete. And this is the classical error correcting scenario. Okay. So what we have is that on Alice's end, she has a message source. Okay. So whatever she's, you can think of Alice herself typing in messages, or you can think of some computer or something that Alice controls, which sends messages that Bob receives. Okay. So the message you can think of as a bit string. Okay. So the message is some bit string of length k. And what happens is that this will experience an error. So what ends up at Bob's end is the message plus this error, right? So the error is also a bit string of length k. M plus e, gives you the message that Bob actually receives. So we can think of something like, Alice sends a message like 0110 or something like that, right? So length k4, and what the error comes out to be is that there's a flip on, say, the last qubit, right? So error can be something like this. So this is indicating that the last bit that is being sent gets flipped. So what Bob ends up receiving instead is 0111, right? So this will always happen, and like if this channel is introducing errors of some sort, this will happen, and Bob can never really tell what Alice meant to send, right? They will always, like, if this is distorted, Bob doesn't know that an error happened or no error happened, right? So it is possible that no error happened, and what Alice sent goes through and Bob receives it, but there can an error can also happen. So Bob is not really sure if this is what Alice meant to send. So he'll always be uncertain, and this is not a good place to be. I think I have a question for you guys, which is that I see a lot of things here. No, that okay. So my question for you guys is, how many possible errors are there that that could occur in this scenario? So many, I see lots of bits. So Vardha says 16. Okay. I'm talking about the math errors. So 16, right? And the reason 16 comes in is because the error is of length k, right? So is length 4. So there are 2 to the 4 possible errors, right? So you can write down all the 16 bit strings that occur, right? So you can put a 1 or a 0 at each of these locations. So that's 2 to the 4. So you get 16 possible errors. Okay. Now, in a real world scenario, this is not what I mean. These all of these 16 possible errors that we can write, right? So I mean, the errors are something like 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and so on, all the way up till 1, 1, 1, 1. All of these errors are not equally likely to occur. They will occur with different probabilities, and a very simple model for noise, which is kind of consistent with the real world, is that your EI is going to be 1 if so, or maybe I should say that my model for noise is that bit I is flipped with probability. Let me erase this, or let me move it. With probability p, right? So each of these 4 bits are independently can be flipped with probability p, right? So what that basically means is that I'll flip a coin, and I'll say that EI. So I'll flip a coin 4 times, and that coin will have heads with probability p and tails with probability 1 minus p, and it will EI will be 1 if my if heads, and 0 if tails, or maybe I should say with this is maybe a better way, with probability p, and 0 with probability 1 minus p, right? So this is quite realistic, and then you can see that that each of these guys has a different kind of error probability. So I mean, let's actually look at some of these cases. So you can see that 0, 0, 0, 0, 0, 0, 0, 1. Then I have something like 0, 0, 1, 1. Then I have something like 0, 1, 1, 1. And then I have something like 1, 1, 1, 1. Right? So if you have single qubit errors, you'll have what is the probability of something like this happening? So 0, 0, 0. What's the probability of that occurring? Well, not 1 over 16, right? So we have to respect this thing. Or you can just think of it like this: bit I is flipped with probability p. Right? So a bunch of people are getting it. So 1 minus p raised to power 4 is kind of the correct answer, right? So none of these guys are getting flipped, right? So all of these guys are getting not getting flipped. So what you have is that the probability of something like this is 1 minus p raised to power 4. Another thing I see in chat is people wondering why this is getting included. Some of these people, some people were excluding this from a set of error. So what we think of this this case when not actually the message goes through without error as also an error, but like the trivial error. So I mean, your math becomes difficult if you try to exclude it and just deal with the remaining 15 things which are real errors, and this is like a fake error, but we'll include it and think of this as a trivial error, which actually is not an error. Okay, so this will be included, and the probability of not error is 1 minus p raised to the power 4. So you can see that if p is small, right? If p is a small number, so maybe you have like only a 1% chance. So this is just 99% raised to power 4. So that's a quite high number that you will actually get, no error. But if p is a large number, then this is flipped, and then you won't get this with high probability. What about this? What about 1-bit errors? What sort of probability is there? So all of these 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, all of these. What are the probability here? Yeah. So people are catching on. So you get 1 minus p cube, right? So 3 of the guys are not getting flipped, and 1 of the guys getting flipped. So you'll say this is coming because of this 1, and this 1 minus p cube is coming from these 3 zeros, right? So this is a different probability. And then similarly, you can see here that this will be p square, 1 minus p square, and 2 qubit errors. And then this will be similarly, you can compute the other 2 scenarios. So these errors are occurring. That's kind of the message here, that these errors are occurring with different probabilities. Okay. And it's for realistic levels of noise, when p is small, generally, right, in the channels that we typically use, this p will be small. So let me actually give you an example of the kind of channel that is used here. So right now, a lot of you are probably sitting on your laptop listening to this talk. Okay, there is a channel from my end all the way to your computer. Okay, what happens in that thing is that whatever voice is being recorded by my computer, it goes into Zoom, and then Zoom sends it towards you. Okay, and then it gets to all the way, it gets to your Wi-Fi router, and then from your Wi-Fi router, it has to go to your laptop. And what ends up happening is that all the messages that your Wi-Fi router sends to your laptop are not actually received. There's the error. Some of the packets that are sent are actually lost. And there are error correcting algorithms that are being used by your Wi-Fi router and your laptop combined together to kind of correct those errors, which is why you can mostly see my talk right now or hear me perfectly. Okay, so there's this all of these protocols, and we'll learn some of the basic ones right now. So and the probability of those packets getting lost on the way between me and you is quite small. Okay, it's not like, realistically, it's again like under 1%, but under 1% is still non-zero, and things will be get lost. If you have a bad internet, then it becomes really high. So if you get something like 5-10%, which happens when you have bad internet, then obviously you stop being able to listen to Zoom call, and things start breaking up and all that, and bad things happen. So if there are no more questions about any of this, I don't see questions. So let's move on and talk about a method for detecting and correcting errors. Okay, and this method is actually quite simple. It's based on the idea of repetition, which is what you actually do. So if you're talking on the phone with someone and it's a bad line, and you tell them something and say, I can't really understand you. So then you repeat it again, and you repeat it maybe like again, so you say the same thing 2 or 3 times just to make sure that they understand it, right? So we already use this idea of repetition to kind of get around errors. So let's think about that. So I've expanded my diagram here and our how things will happen. So you can see now that Alice is generating these messages, these length k messages, but this is not what she's sending to Bob. So what she does is she has a thing which is called an encoder, which is going to transform these messages, these length k messages, into length n code words. Okay, so this is our first piece of jargon that we are using. So this is this code word is a longer thing, right? So here we have the idea that n is typically larger, and often it's much larger. So it can be several times k. Okay. And then this code word is what goes through your noisy channel, and then is obviously subjected to an error. And then there's a corrupted code word, right? So the corrupted code word is the addition of C plus E. So this is what Bob receives. So Bob has to look at the C tilde, okay, and figure out what message Alice sent. And so he has a decoder that tries to estimate a message m hat that Alice sent. And what we will see is we'll do a probability analysis in the notebooks, and we'll see that this, like if you do this correctly, if you do this encoding and decoding correctly and cleverly, you can you'll do better than the scenario. So the kind of errors, the percentage of the time Bob receives the correct message here, which we actually computed, which was 1 minus p to the raised to power 4, he will actually do better in this scenario, and the probability for receiving the correct message will be higher. Okay. But to do that, we should well, okay, let me just say things abstractly first, and then we'll jump into detail. So why would the probability be better? We can see that this is a longer message, or this is a longer thing. And what we are doing is we are adding some sort of redundancy to our message. You know, perhaps we'll repeat it, or we'll store some information about the message that will allow Bob to recognize that some errors have occurred, and it will give him a pathway for correcting the errors. Now, these because these code words are longer, okay, so the probability of non-trivial error, of large errors that affect a lot of different bits in this code word will be smaller here than in this scenario where this is a shorter string. So because this is a shorter string, the probability that 2 or 3 or 4 different errors happen is quite large. But as you make your string longer, the probability that you get like 50% of your bits being destroyed or being flipped becomes much less, right? So if you do this encoding correctly and decoding correctly and cleverly, then the probability that your message is still inside this corrupted code word and it can be extracted, that probability is much higher. Right? So this is quite abstract. Let's actually work through the mechanics of this repetition example, and it will become a lot clearer. So let's take an example. So suppose that Alice wants to send a message. So let's set k equals to 2, okay, for now. And what we will do is we will say that message that Alice wants to send is perhaps 0, 1. Okay. Now, in the repetition case, okay, this is what we are looking at. We will have n equals to 3 times k. Okay, and the way it will work is that what this encoder does. Okay, so what this encoder does is whenever it encounters a 0, instead of sending a 0, it sends a 0, 0, 0. Right? This is your repetition. And whenever Alice tries to send 1, the encoder actually sends 1, 1, 1. Right? So what happens is that if Alice tries to send 0, 1 as her message, okay, it will get transformed into the code word 0, 0, 0, 1, 1, 1. Okay. So this is quite simple. Yeah. Okay. No questions on Discord. So this is the kind of code words you get, and you can generalize easily, right? So if you have a longer message of some sort, then this will be longer. Just you just repeat each of the bits multiple times. Okay, so errors could happen on this. So let's look at the scenario. So let's imagine error here. So error could perhaps be, let's put an error perhaps on the second guy. Right. So this is an example of a non-trivial error. The second bit is getting flipped. Under this error, what happens is that my C tilde actually becomes 0, 1, 0, 1, 1, 1. Okay. So this was my encoding. This was my noise. And now we have to apply the decoding, right? And you can see quite easily that if you have something like this, the message is kind of still in there. So what do you think we do? Parity check, debug. So what do you do? Like when you look at something like this, imagine you are the decoder here for Bob, and this is the message you receive, and you know that this is how encoding was happening, right? So you're aware that this is the encoding that's happening. How do you go? How do you estimate a message M hat from this? Right? So you look at the majority of things, right? So it's quite clear that from this, your decoder will be that M hat is, you will look at each set of 3 bits, right? And you will say that, hey, the first set of bits is giving me 0 because the majority of them is 0, and the second set of guys is giving me 1, right? So maybe I don't need to draw these many arrows. Right, so I'll Bob, the decoder and Bob else will just look at sets of 3 bits and take the majority of them to something like that. Obviously, this can go bad, right? So let's again look at the same example. So M is equals to 0, 1. My code word is actually 0, 0, 0, 1, 1, 1. Now my error is this time going to be 0, 0, 0, 1, 1, 0. Right, so this is telling me my corrupted code word is actually 0, 0, 0. Sorry, there's a mistake here. 1. So these guys will get flipped, right? Because my error is occurring. No, what did I do? This I am getting. So these 2 bits are getting flipped, so these 2 guys get flipped, and you get something like this, right? So you get something like this, and then when you decode, right, M hat will obviously be 0, 0, right, which is unequal to M. So this is not a perfect process. The same way when you talk on the phone and repeat yourself, it's not necessary that the person on the other end understands you, but it does help. And in this case, we can see that the only time you can correctly decode is that within each block of your code word, there is only 1 error, right? So you have 2 blocks here, and within each of these blocks, if you only get 1 error, then you will correctly correct, and if you get 2 errors in, or then you will, or even 3 errors inside a block, then you will definitely make a mistake. Okay, so why doesn't 110 get corrected to 1? So this is not 10. This is my error, right? This is not Bob does not know what the error is. Bob, this is a physical process that is happening. What Bob receives is this guy. He receives 0000001, right? Because when you distort this guy by the error, you get this, right? So, and then when you look at this, you get 0, 0. So, so now there's a probability question here, right? So we need to look at. So, so there's a bunch of tasks, right? So you're familiar with how these QWorld notebooks work out. So you write some code to do this encoding and decoding as well, and then you will figure out in task 3 what the various probabilities are and whatnot, and then you'll plot it. But let's kind of go over it. So probability of success. So my blue is my naive method, right? Or what I should call no error correction. So this blue line is this no error correction method, right? Because remember that the if you send one bit through here, right, in this scenario, when you're not doing any sort of error correction, right? So you send one bit error. If you send 0, then there's a probability P. There's a probability P that you will get 1, right? And a probability 1 minus P that you will get 0, right? So this P, I should probably have written that this P is the probability of error. Let me just check. Yeah. So probability of error, right? This is what I'm calling my probability value. So, and the same thing happens if you have 1 here, then obviously, you get 0 with probability P and 1 with probability 1 minus P. So probability P is our probability of error. So when we depending on I mean how this goes, basically as your probability of P, this is P on our x-axis, on our x-axis, as probability P goes from 0 to 100, our probability of incorrect inference by Bob will also go from 0 to 100, right? So this is our naive method. Now, if I do the repetition method, so I'll let you do the calculations yourself, but what you will discover is that obviously you start from 0, because if your probability of error on your transmitted bit is P, then your probability of incorrect inference will also be 0. But what will happen is that you will get something like this, okay? Where the crossing point is obviously at 0.5. Okay, so this point is 0.5. Sorry for my horrible rhyme. And you can see that when the probability P is small, is less than 50%, then your probability of incorrect inference by Bob will actually be less than the naive method, okay? But if your probability P is large, then actually you'll do worse with this repetition method, and you'll actually Bob will will infer the wrong message, with actually higher probability than actually not using error correction. And this is actually the reason why when Zoom calls or Skype calls or whatever, when there's bad internet, they become so bad so quickly, right? Sometimes you get a little bit of error, and that's fine, right? You some of maybe a little bit of things you can't understand. But if your internet goes a little bit worse, then suddenly you can't hear anything, and you can't see anything because everything is kind of garbled, and you get lags and whatnot. And that's exactly what's happening. Like the threshold there in those more sophisticated algorithms that Zoom uses are different. This 0. It won't be 0.5. It will be some different error. Actually, the probability will be quite lower. So what happens is that when your internet is so bad that your probability this crossing point is actually is crossed, and you're in this regime, then things become really bad and you can't hear anything at all. Okay, so let's see what's on this one. Yeah, so I mean, a good way of saying it is that it is indeed good that if a lower number of flips happen, and it's bad if a higher number of flips happen. Well, no. So Valerie is saying that Zoom is just a software app and just it receives a transmission and just shows it or something. Channel is actually the network connectivity. That's not true. So there are when you do transmissions on the internet, there are multiple levels at which error correction is happening. Error correction happening at the network level, but Zoom itself uses error correction on top of that, its own error correction on the video encoding, which is supposed to improve. Which is why you can see, like, I don't know, if you use some bad app, like if you I don't know, if you used Skype like 10 years ago, something like that, or some other app, their error correcting algorithm was not so good. So like when you had bad internet, you would get really bad transmission on those. I'm sure people know Skype. Skype is not that old. Okay, so I think I've answered the questions, and I think you get. And my goal here is obviously just give you a sense of how things are. I don't want to kind of get in the way of learning. I mean, this is supposed to be an overview. So you work through these things and you plot things, you calculate and plot things here, and you will understand these things a lot better. Okay, so let's kind of move on and talk about this more abstractly. So we have we've looked at one simple scenario. Let's look at what kind of error correcting procedures we can construct in general for classical error correcting, right? So the scenario is still the same, right? So there are messages, there are encoders, decoders, and whatnot. Now, let's think about this process of encoding abstractly. Okay, so you have messages, and we just saw that when k was 4, there were 4 messages. There were 16 messages, right? 2 to the 4. So the space of all possible messages is called our message space, right? So our messages live inside this message space, and we want to describe these mathematically. So for that, what we need is the concept of a so the numbers here are bits, right? So our numbers are bits. We technically in mathematics we call this, we are dealing with the field whose elements are 0 and 1. Okay, and the addition and multiplication, maybe I can make these slightly bigger, is given by these two tables. So you can see that what it's saying is that I mean, this is quite familiar. So it's saying that if you add 0 and 0, you get 0. If you add 0 and 1, you get 1. And this guy is also saying the same thing, that if you add 0 and 1, you get 1. But now you have the anomalous case, which is that 1 plus 1 is actually equal to 0. Okay. So this is you have to keep in mind. Multiplication, on the other hand, is exactly how we are familiar with, that if you multiply either 0 or 1 with 0, you'll get 0. And when you multiply 1 by 1, you get 1. But this anomalous case of 1 plus 1 equals to 0, you have to keep in mind. So instead of writing these messages as just bit strings, I wrote them as strings of zeros and ones. I can also write them as vectors, right? Or so I can write them as vectors, and this is how I will often write them. And when you do computations in Python and stuff, you will also do this. So we can ask ourselves, what is v plus w, right? So you can think of this is a message and this is another message, and I'm adding two messages together. So what I'll get is 1 plus 1 is actually equal to 0, and 0 plus 1 is equal to 1, right? The other thing we can do is obviously matrix multiplication. So we can compute something like m w, for example, right? And you can see that what will end up happening is that when I multiply, let me quickly write down w here so it's easy to see what we're doing. So you can see that I do 1 into 1 plus 0 into 1, and then I do 1 into 1 plus 1 into 1, right? And then I get 1 plus 0, 1 plus 1, which is actually equal to 1, 0. Okay, so this I'll remove so we don't get confused. So this is the kind of linear algebra we will do, right? So instead of thinking of these as integers, and doing 1 plus 1 equals to 2, don't make that mistake. So whenever you have 1 plus 1, you'll add 0. You'll turn it into a 0. So you'll get things like this. I hope this is clear. Yeah, so we are just using modulo 2. I think everybody's familiar with modulo. Perhaps I should use that terminology. I mean, technically, it's not modulo. It's just a field with these operations that is fine, but that's fine. So now what we are getting is that let's get back to our abstract picture. So messages are living in this message space. And what we do is we write this guy as f, okay, with a fancy f. Maybe I can try to squeeze it better. Okay, so I'll write a fancy f for this guy. And these guys, so v and w, are actually, so sorry, there's a 2 here. I forgot. So 2 indicates there are actually 2 numbers inside a field, or you can think of it as a modular 2 as well, which also works. So v and w are actually members of, I'm going to write square because they have length 2, right? So they are something like this, and obviously if you have some v which is 1101, then it is a member of f24. Okay, so this is a vector space of dimension 4 over the, so this thing is called the binary field as well. Okay, so not binary fields, but binary field. So over the binary field. Okay. So all the things that you know about vectors and vector spaces continue to hold for things like this. So you can see, I mean, you can, if you have two elements in abstractly in VW in f to the 2n, then you know that v plus w is also in this guy, right, for instance. Or you also know that if you do 0w, that is also in here. If you do 1 times w, this is also in this guy, right? So all their standard properties. You know there's an identity element, so w plus 0 vector, right? So maybe I should just put some vector signs on them, so to distinguish them from scalars. So this will also be equal to w, right? So all the things that you're familiar with vector spaces all continue to hold. You should check this. If you don't believe me, you should check that if you do this kind of addition and multiplication, I mean, these axioms or these properties of vector spaces continue to hold, and nothing bad happens. So coming back here, so your message space is given by these 2 to the k, right? So this is actually, so what we have learned is that the message space is actually a vector space of size of dimension k over the binary field, and you know it has elements which are of length k, and it has, you know, the size of, you know, of, so I can write my size as like this, right? This is equal to 2 to the k, right? So there are 2 to the k possible messages. And on this end, you have, what you see is that you convert this into, by encoding into bit strings of length n, right? So all this space is f to the 2n. Okay, so it's the vectors, it's vector space of length n over the binary field, and all your corrupted code words and your code words, they all live inside this space. Okay, and what we discover is that, I mean, because there are only 2 to the k of these messages, each of these is, and there are 2 to the n of these elements in code space. There are a lot more elements in the code space compared to the message space. So only you get this subset, and this subset, right? This subset. So the code obviously has size of 2 to the k as well, right? There are 2 to the k elements in this code, and each of these messages is being uniquely mapped onto one of these codes, right? So these elements are length n, but there are 2 to the k of them. So code, I mean, I should specify that code. Let me add a thing. Code is a subspace of the code space. Okay. So this is what an error correcting code is. It's a subspace of your larger code space. And the way it's designed is that just cleverly designed, that you place it in the right location. You pick the right 2 to the k elements inside your larger case code space, so that decoding actually is possible, and you can extract the right message with high probability from the corrupted code word. So what happens is that the impact of errors is that whenever you have a code word C that goes through your channel and experiences an error, if it experiences a non-trivial error, okay, sorry, if it experiences a trivial error, which is all zeros, right, no error, then it will stay in here. If it experiences I mean a non-trivial error, then it's likely to go outside this code space. But this is actually not true. Let's look at this in detail. So what I want to do is I want to draw this again. Oh man. Let's look at this for repetition code. Right, and what I'll do is I'll say that my messages are actually like length. I'll for repetition code I'll set k equals to 1 and n equals to 3. Right, so we'll only sending messages of length 1. So you're inside your message space. There are only 2 elements. There are oh man, my software sometimes gets stuck. Okay, sorry about that. 1 second. I have to delete this. Sorry, I have to. Sometimes when I copy the when I copy pictures inside the app, it sometimes crashes. So repetition code, yeah, so it's good. Repetition code, and I'm going to set k equals to 1 and n equals to 3, right? So we'll send only 1-bit messages, and they'll obviously get transformed into length 3-bit strings. So there are only 2 things here. There's 0 here and there's 1 here, right? And there are only 2 things here, 0, 0, 0 and 1, 1, 1 here, right? So 0 gets mapped onto 0, 0, and 1 gets mapped onto 1, 1, and everything else is in here, right? So 0, 0, 1, 0, 1, 0, 1, 0, 0, right? These are the 1-bit scenarios, and then you have 0, 1, 1, 1, 0, 1, and 1, 1, 0, right? So there are 3 plus 3 plus 2. That's your 8 possibilities. So what is the impact of different kind of error? I just want to belabor this point, that if you get if your error is 0, 0, 0, right, then these guys stay where they are, right? If you get an error which is, is 1 flip, okay, let me write it like this. So what you will do is that these guys will go over here or over here, right? So 0, if the error, if what you sent was 0, 0, 0, and then you get 1 flip, you can either get 0, 0, 1, 0, 1, 0, or 1, 0, 0. But if what was sent was 1, 1, then 1 error will obviously get one of these guys, right? So if the first bit gets flipped, you get 0 here. If the second bit flipped, you get this, and if the third bit gets flipped, you get this, right? But if you get 2 flips, your things are reversed. So 0, 0, 0, 2 flips means that you get one of these guys, right? The last 2 bits get flipped, or the first or the last bit gets flipped, or the first 2 bits get flipped, right? So now in this scenario, you're going from here to here, and 1, 1, 1 is actually going over here, right? 2 flips will take 1, 1 to one of these 3 guys. So which is why you can't fix 2 flips. This is I think it should be clear now that you can flip these guys because this does not distort anything about your code words. This takes the zeros to over here and the 1s to over here. So you can tell the difference between what happened, right? So you can go back from here to here or go back to here. But if 2 flips happen, then you get mixed. This goes here and this goes here. So then you make the incorrect inference. So if you run the majority voting algorithm on this, you say that, oh, 111, it was 1 was actually sent, but actually 2 flips had it was actually 000, which got flipped twice, which got you here. And then actually the third case is just as bad, which is 3 flips, which is that 000 gets mapped onto 111 and 111 gets wrapped onto 000. So these get exchanged, which is really bad, because then your corrupted code word is still inside your code, but you know, like the code words got exchanged in some way. So you make the incorrect inference. Okay, so I hope this is clear. Let me look at. Yeah, so sorry. So Ron Shearer says that IF is F, so I should probably just point it out in the notebook that, yeah, you can see over here, this guy, right? So over here, so it's a fancy F that I'm writing by hand. And the also asks drop packets that have 2 flips. Well, you will you don't know how many flips they are, right? Remember that you don't know what error occurred. That's the whole problem. Like something goes to the channel and Bob receives something. He doesn't know what error happened. He just estimates a message, and if it's wrong, then, you know, in the case of video, things go really bad and you get black screen instead of something interesting. Yeah, so if there are 3 flips, like, it's really bad, because like your code words have flipped around, and you like it's in the quantum case, we'll see that it becomes really problematic. There's another interesting comment by Hamid. So Hamid says that the closed space, which is, I should just point out that when we're looking at this, the idea that is the code is a subspace, and it's a which means it's closed, right? If you add 2 code words together, you'll get another code word. This is, I mean, this is, we won't really use it that much directly, but it's an interesting fact that you should remember. So I've realized that I'm going quite slowly. I should speed up and go through the 2 things. So let me just, I mean, talk about this encoding process a little bit more in just one minute. So right now, what we said was our encoding process was that if you see 0, you encode it into 000 and 1 into 111. But I want to have a linear algebraic method of doing this, right? So what I'm going to do is encoding process using linear algebra. Okay, so my messages are now going to be vectors of length 1, right? So this is a vector of length 1. This is another vector of length 1, right? And these are, let me just specifically say that these are row vectors. Okay, my messages are going to be row vectors, and when I look at the next scenario, you'll see that, you know, I'll write rows instead of columns. And what I'll do is that there's a generator matrix for the code. And what does the generator matrix in this case look like? I'll just say it's 1, 1, 1. Okay. In general, it is k times n, right? So for the repetition code, so I mean, right now we are looking at the repetition code. Code as an example, so which has k equals to 1 and n equals to 3. Okay, so you can see that it's a 1 by 3 matrix, and then the encoding process is that your C is actually m times G. Okay, so we are going to put our vectors on the left and our matrix on the right. This is, this is how things are done in like classical coding theory. So I'm typically done in coding theory. So I'm writing it like this. There's no problem with switching things around, reconstructing it. So there's right multiplication, but this left multiplication, kind of where your vectors are on the left, is how things are done. So you can see, for example, that if I do 0, 1, 1, 1, right? So this is my message, and this is my generator matrix. You can see that I'll do 0, 0, 0, 0 into 1, 0 into 1, 0 into 1. For each is my columns. I'll get 0, 0, 0, which is indeed my correct encoding. And then if I do 1, so I get 1, 1, 1. This is my, and then I get something like this. Okay. So this is kind of, I don't see any question in Discord. So this is quite a simple process. We'll see an example of this when we look at a non-trivial code. Okay. So let's look at a bigger code where k is not actually equal to 1. So we can see bigger matrices. So this is the Hamming code. Richard Hamming is a mathematician and very famous mathematician. If you look at his Wikipedia page, there are about like 30 things named after him, because he was so he produced so many different research results that and everything got named after him because he was the first in so many different areas. But he was one of the pioneers of this error correcting field as well. I think he did this in the 50s, if I'm not mistaken. So 1950s. Anyway, he invented this Hamming code, which is one of the nicest codes you can do, and we'll see this code over and over again. So in the quantum case, we look at what is called the steam code, which is actually constructed from the Hamming code. And this is quite common, that quantum error correcting codes are actually constructed from classical error correcting codes. And so this is one of those, which is why we're studying this. So here in the Hamming code, your k equals to is 4, and your n equals to 7. Okay. So your messages are vectors of m1, m2, m3, m4. Okay. And you want to convert them into a code word. And the process for this is simple. m1, m2, m3, m4. Your code word is going to be, you're just going to copy the first 4 bits, the message right into the code word, and then you will attach these are parity bits. Okay. And what these parity bits are given by this kind of Venn diagram, which makes it quite easy to see what will happen. So the idea is that you look at P1. What is P1? P1, so you can see that I have 3 circles. P1 is at the center of this circle, P2 is the center of this circle, P3 is the center of this circle. And M1, M2, M3, M4 are put in the intersection of these circles. Okay. So what this says is that P1 is actually M1 plus M2 plus M4. Okay. So from the diagram, we can see that P1 is actually M1 plus M2 plus M4, right? All the M's that are inside this P1 circle. And then similarly, you can see that P2 is actually M1, M3, M4. And then P3 is equal to M2 plus M3 plus M4. Okay. Now, and these are called parities because it tells you whether the sum. So why they're called parities? Because it tells you. So P1, for example, is telling you whether the sum of M1, M2, M4 is 0 or 1. Okay. So for example, if M1, M2, M4 were all 0, then the parity would be 0. If one of them was 1, then you would get parity of 1. if two of them were 1, you know 1 plus 1 is 0. So for example, if these two guys are 1, then 1 plus 1 is 0, and then 0 plus 0 is 0. So parity is 0. But if 3 guys are 1s, then again you get 1 plus 1 plus 1, which is actually equal to 1 according to our algebra. So parity basically tells you how many 1s there are, right? If they're even number of 1s, then your parity is going to be 0, and if they're odd number of 1s, then your parity is going to be 1. Okay. And this process of storing these three different parities is enough to correct any single bit flip, one bit flip on your code word. So let's kind of go over the different cases. So imagine for a second that M1, right, the first guy is what encounters an error. Okay, so what Alice will do is Alice will create this guy, right, and send it to Bob. Now there'll be error, and we're saying the error is on this guy, right? So M1 is getting an error. So what Bob will do is Bob will look at the corrupted code word, right? And for him, like, I mean, in the scenario, let's write this down. So error on M1, right? So C tilde will be M1. So I'll just write prime. Sorry, there are no commas. I should just write them as is. M4, P1, P2, P3. So this is a prime because M1 is where the error occurred, right? So now what Bob will do, his process will be, he will compute the parities again. He will have the same diagram, and he will not look at these guys. He will say he will look at these first 4 guys and compute parities. So Bob parities again, right? So he will compute P1 Bob, which is equal to C tilde 1 plus C tilde 2 plus C tilde 4, right? So same way he's looking at the first 4 bits in his code word, and he's computing the parities in the same way, right? So same formula, but instead we have C tilde. And he will compare with, in this case, P1, or I guess with C, this is C tilde 5, right? P1, which was stored in C, is the 5th element of C tilde, right? So he will compute this guy and compare this, and then he will compute P2B, and he'll compare it with C6, and he'll compare P3B and compare it, and see what happens. So now let's go back to this diagram and see what this kind of process means. So our error is on M1. What will happen is that P1 and P2 will actually change their value, right? So the P1 and P2 that Bob computes will change their value, right? So when Bob compares those values to the P1 and P2 that Alice sent, he will discover that these are different. And he'll look at this diagram and he'll say, oh, P1 and P2 are what are getting flipped. So that means M1 is the error. And you can see this process works for any of these scenarios because it's symmetric, right? If M2 encounters an error, P1 and P3 will fail for Bob. And he will realize that M2 is the bit that got flipped. Similarly, for M3, P3 and P2 will get flipped. And for M4, all of them will get flipped, right? Because M4 is involved in P1, P2, P3. So all of them will get flipped. So if all of the parity bits are getting flipped for Bob or coming out incorrect, then he knows that it's M4, which is the problematic bit. Mohammed Reza, I don't understand your question. There's something of P1 out of M1, M2, and M4, isn't there? Sorry, can you please ask again? Hamid, you had an earlier question if all elements of G must be 1. So sorry, this is going back. This is in the repetition case. No, they don't have to. People will see, in fact, the the generator matrix for Hamming code is written here, and you can see it's zeros and ones. So I don't see questions in Discord, so I'll let you think about it. But let's think about what happens. The errors can also happen on these guys, right? So P1 or P2 or P3 could also be the ones that get flipped. So if P1 gets flipped, okay, and so Bob will compute, for example, P1 Bob, which is C1 tilde, C2 tilde, C4 tilde. There are no errors on these guys, right? So in that case, right? So in that case, there's no error here. The error is over here. So the parity of M1, M2, M4 will still remain the same. So what he will discover is that P1 Bob is incorrect, P2 Bob is correct, P3 Bob is correct. So if only one of the parity bits is coming out incorrect, that means that it's actually the parity bit which got an error, and that's not a problem. Like Bob doesn't actually care about the parity bits. He only cares about receiving Alice's messages. So he will just do this. He will just take the four guys, and he will say, "Oh, I'm good." And you can see this works for P2, P3 as well. That if the error is on the parity bit themselves, then only that parity bit will be the one that will be inconsistent for Bob. The others will be fine. So so Bob knows the error is on the parity bits. But if there are 2 parity bits or 3 parity bits which are inconsistent with what Alice sent, then he knows that the errors are on the message bits, and he looks at this Venn diagram to figure out which one it is, and he just corrects it. So do we have to share this Venn diagram of parity? And before, yeah, so Alice and Bob before, so it's assumed that before they start communicating, like they have met at some point, right? And they've agreed upon the process for encoding and decoding. So, I mean, in our Zoom example, so we all download the Zoom from zoom.com or whatever the website is, right? And we install it. So that is our agreement that we are all using the same error correcting protocol that the Zoom app is providing, which is why Zoom and Skype can't talk to each other, because the algorithms are different. So I hope this is clear, this abstract process. Think about it if it doesn't make sense. But what that ends up happening is for this is that let me just not try to encounter error. And we don't need this here anymore. Yeah. So I copied my mouse as well. My mouse is still here. Okay. So this is the generator matrix for Hamming code. Okay. So it's quite easy to see why this is working. So you can see that there's identity on the first 4 guys, which is exactly what we're doing. We are saying we are just copying the message bits as is. And then what we do is we add various combinations of the messages together. So let's kind of try to do this. So let me copy again. And let's look at an example. So for example, Alice wants to send the message 1010. Okay. So this is my message. This is my G. And now I'll get my code word. So you can see that when I multiply this guy with the whole row, with the first 4 row, I will only pick up the first guy. When I multiply this with the second column, this row with the second column, I only pick up the second guy. Then I pick up the third guy when I pick up the fourth guy. So I'm just copying these things down. And then when I multiply this guy with over here with the fifth guy, you can see that this is saying that add the first, the second, and the last guy together and write down the result. This is my parity, M1 plus M2 plus M4. right? So m1 plus m2 plus m4 is 1 plus 0 plus 0, which is actually 1. Similarly, I'm saying first guy, third guy, fourth guy, compute the parity m1, m3, m4, right? So this is 1 plus 1 plus 0, which just gives me 0. And then this is saying m2 plus m3 plus m4. So last three guys, and you can see the parity of this. You just have to count the number of ones, right? So there's only one 1 in the last three guys. So my parity must be 1. So this is your linear algebra way of doing this. Quite simple. And you can write a general encoder. So if you have this, like obviously, well, I mean, when Alice and Bob implement an algorithm, which you will also do in the notebooks, you'll just construct the generator matrix, and from that generator matrix, you just multiply your message and you get your code words. Okay, so final thing before we stop. Well, yeah. So I mean, I've told you how to do encoding, right? Encoding process, what that is. But now I want in a linear algebraic way, right? So you can see that this is quite easy. Like you put in a message and you get a code word. But now what we want to do is we want to figure out a well, maybe not systematically, not best way, using linear algebra, right? So how do I do linear algebra? Do some matrix multiplication of some sort and correct my identify and correct errors. So for that, to identify errors, we need the parity check matrix. Okay. So H, okay. Right, and the parity check matrix is defined to be well, so this is a n minus k, n minus k into n sized matrix. And the way to think about this parity check matrix is that when we do this encoding process, we go from this message to this code word. What we do is that we, like, I mean, this is Hamming code is quite simple in that we copy the messages as is and then add some parity checks. But in general, you don't do it. I mean, you don't have to have an identity matrix in your generator matrix. You can have other generator matrices where all the columns are non-trivial. But what you do is that you construct this code word in a way that it obeys some constraints. Okay, there's some relationship between the different elements of this code word, which is what allows Bob to figure out where the error has occurred, right? So those constraints, whatever those constraints are, we can express them in linear algebraic terms. And we can say that, hey, these are the constraints, and you check each of the constraints and some of them will fail. So here you can see that we have 3 constraints, okay? And in the parity check matrix, there are 3 rows. Each of these rows is corresponding to a particular constraint, okay? So you can see that now for the Hamming code, n was equal to 7, k was equals to 4. So n minus k is equals to 3. So you have a 3 times 7 matrix here, okay? And basically the idea behind the parity check matrix is that it is constructed in a way that h times c is going to be 0, and h times non well, c tilde is not equal to 0, where I'm going to specify that that C tilde is corrupted code word with non-trivial error. Okay. So I mean errors that actually moved your code word out of your code. Maybe that's the more correct thing. But basically the idea is that these are the constraints that are occurring. So we can kind of see this here. So let's look at what the first row is saying. The first row, let me write down the M1. Maybe if I make it bigger, then I can actually write it. Yeah. So if I write down M1, M2, M3, M4, P1, P2, P3. So look at what this guy is saying. This guy is saying that the check that Bob has to do, he has to compute M1, M2, or well, of your code word, he has to compute the first, second, fourth guy, right? M1, M2, M4, and compare it with parity P1 or the fifth guy, right? So, I mean, you can see it from here that when you do this comparison is basically checking. Like if what Bob computes and what Alice sent were the same, right? Then P1B plus P1 will actually be equal to 0, right? If both of these are 0, then 0 plus 0 is 0. And if both of these guys are 1, then 1 plus 1 is equal to 0. Right? So if what Bob computes, this parity is not flipping, then P1 and P1B will be the same, and their sum will actually be equal to 0. But they are different, right? Then if this is 0 and this is 1, then 0 plus 1 equals to 1. Or if this is 1 and this is 0, then 1 plus 0 is equals to 1 as well. So basically, that's what we're doing here. We are saying that M1 plus Bob will do M1 plus M2 plus M4 and then compare with the first parity bit. So you'll add. And if it's 0, then that parity bit has not flipped. And if it's 1, that means that that parity bit is inconsistent with what Alice sent, and he has to check it. So this is, you can kind of see it here that we will do h equals to 0, and we'll get something like this. So we can do an example here. So I mean, we just did the let me do it with blue. We had the message 1011, right? No, 1010 in the previous slide. And the parities were, well, did we do explicit example? We didn't do explicit example. Do I need to do an explicit example? Yeah, let's do an explicit example. So let's see. Let me do it on the next page, I think. So we have some space. So let's see that M is equals to 1010. Then my C was equal to 1010, 101, 1010, 101, right? And then let's say error on first guy. So my C tilde will actually be 0, 0, 1, 0, 1, 0, 1, right? So only the first guy has been flipped. Now what I'm going to do is I'm going to go down to my parity check matrix, copy it. Yeah, so people are already seeing the relationship there. So what we will do is we will, right? So we'll do 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, right? So we will do this kind of multiplication, right? HC tilde, and we'll compute. Actually, yeah. So let's just compute it once, and then I'll tell you the general relation here. So you can see that we are only, when we multiply 1 into 0, 1 into 0, 0 into 0, 1 into 0, 1 into 1, and then everything else is 0. So there's only one place. So I think this linear algebra is quite easy. Basically, you look down here and see where these ones coincide. That's the only place where you can have a 1. So this is the only place where ones happen. So you can actually get a 1 here. And then if you look at this guy, you can see that the third spot has a 1, the fifth part has a 0, and the last spot has a 0 as well. So you can see that this guy is also 1. And then we will look at this guy. The third guy is 1. The fifth guy is a 0. And the last guy is a 1, right? So you get 2 1s. So 1 into 1 and this 1 into 1. So you get 1 plus 1, which is actually equal to 0. So you get this. So this is called your syndrome. Okay. And this is telling you that P1 and P2 are the ones that got flipped. And therefore, you have to go back and fix M1, right? That's what we look at from the Venn diagram. So if I hope this is clear, right? No, so Ron is asking a question, is the decoding M equals to HM? No, so decoding is not HM. So what you do is you construct S, which is equal to H times C tilde. And let me just do it abstractly for a second. So let's just do this. So you have H times C tilde. Remember that C tilde is actually C plus E, right? And then I can just distribute my matrix into vector calculation over the two vectors, right? But what is this? HC. We said that HC is always equal to 0. This is how actually the parity check matrix is defined, that HC is always equal to 0. So this is actually equal to 0 plus HE. So basically, we are computing HE here. And you can go back and you can check that if I multiply H with this guy, with E, sorry, H with E with 1 0 0 0 0, I will exactly get this again. So H times C tilde is actually equal to HE. So basically, and this is equal to the syndrome S, and the syndrome tells us what sort of errors have occurred, right? Here you can see that syndrome is actually length 3, right? So for the Hamming code, so S syndrome is length n minus k, right? This is just coming from matrix multiplication. For Hamming, number of syndromes is 2 to the n minus k, which was equal to 2 to the 3, which was equal to 8. Okay, so there are 8 different syndromes that you can get, and they correspond to the errors that Bob can actually detect on the thing. So basically, I can tell you what those syndromes are. You can. It's actually not hard to see from over here that there are 7 columns here, and each of these columns is a syndrome. And there's a last one syndrome, which is 0 0 0, which corresponds to no error at all. And each of these is telling you something. So this is P1 and P2 are getting flipped. This is saying that P1 and P3 are getting flipped, right? So we said that if P1 and P2 are getting flipped, M1 is where the error is. This is saying P1 and P3 are getting flipped, which means that M2 is the one where error is. This guy is telling us that M3 is where the error is. This is telling us where M4 is the error is. This is saying that the parity bit got an error, parity bit got an error, parity bit got an error, right? P1, P2, P3. So the 7 columns are and plus the all 0 thing, which actually corresponds to no error, are the 8 possibilities that happen. So once you get the syndrome bit, then you have to actually kind of do in general you can go back to the generator matrix, and from the generator matrix you can kind of invert and figure out what the correction is. But that part is not difficult, and you can kind of look at the notebooks where there is. But I would like to stop here now and just open the floor for any final questions and see what we have. So will we have these slides? Yes, obviously. The lecture is being recorded, I think, so it will be on YouTube, and you'll get it there. What is the relationship between n and k? I mean, how to select the size of n and how many parity bits is required when k is 32 bits? That's a great question. So we are not doing that. So that what you're asking is, how do I design good quantum error correcting codes? Good classical error correcting codes. And that is kind of outside the scope of this 4-module class. Right now we're just going to evaluate the error correcting codes that other people have invented and see how they work. But I mean, as you learn this thing, you get a sense of what like how do you construct them so they're good. They're good additional properties. I've not really talked about what makes an error correcting code good and nice to work with. So I see. So sorry, he's asking for the what is the how? So the question is, how do you, if your message is, for example, not 4 bits, it's actually 32 bits. What do you do? So the answer is in your notebooks. Basically, what you do is that if you have a long message which is actually not equal to 4, for example, in the Hamming bit case, you actually break it up. You break it up into blocks of length k, and then you apply the Hamming code to each of those blocks separately. Okay, so if your message is actually 32 bits, then you apply the Hamming code 8 times, and then you send 8 blocks to Bob, and he decodes each of them separately. So there's the other thing. Okay, so that's one answer. The other answer is that Hamming code, that's one thing you can do. You can break it up into blocks. The other thing is that Hamming code is actually not an isolated code. There's actually a whole family of codes, okay? Which means that there's a collection of codes that have the same kind of this property of this Venn diagram kind of situation where you're computing the parities, and they're all called the Hamming codes. They have n different n's and k's, and you can look that up on Wikipedia. I think if you go on the Hamming code Wikipedia page, you'll just see what those relationship is. We're not really interested in that relationship for ourselves, so we won't go over it. Durgesh, so how will we invert this, right? So I think you're asking about how do I go back from the syndrome to figuring out what the how do I, sorry, I think maybe the nicer question is, if I have the code word, how do I go back to the message? So you basically have to do Gaussian elimination on this on GNC simultaneously, right? Remember that you can do inversions on matrices by doing Gaussian so some Gaussian row operations on them, and that kind of works. We don't really care about doing that here, so we won't actually do it in the notebooks. But because finite field Gaussian row operations are kind of annoying, or use a Python library. Well, yeah, I mean, I think there are libraries out there that do it. Not very nice libraries that I found. Does Hamming code only identify the errors? No, it can correct. So once you have the syndrome tells you where the errors are, right? So P1 and P2. So you go back to your thing, and you know that P1 and P2 means that M1 is where the error occurs. What you do is you apply. So maybe there's, I should just say one more thing, that if once you identify location of error, then you do C tilde plus E to get back C, right? So for example, in our case, we just, for example, just discovered 1, 2, 3, 4, 5, 6, 7. Yeah. So you will get the C original, right? So you'll get what was it? Yeah. So you'll get 1 0 1 0 1 0 0. So 1 0 1 0 1 0 1. So you'll get back this, and from here you can just read off the message and say that this is your message. Yes, so I should explicitly say that again. I did not write it down. Hamming code can correctly identify 0 errors or 0 bit flip, or maybe, okay, 0 or 1 bit flip errors. Okay, so if you get errors on 2 locations or 3 locations or 4 locations or 5 or 6 or 7, Hamming code will fail and you'll get the wrong answer. But if you have 0 or 1 errors, then it works. The interesting thing for you would be to, this is not part of the notebooks, but you can compute the error probabilities and see what happens. Okay, so I think Marlo is suggesting to me that I should stop. I think she switched the thing, so we will stop now, and we will you can ask questions on the on Discord, and I'll try to answer them. There's I guess a QEC module and or channel. Okay, and thank you so much for listening to me rant for an hour and a half, and I'll see you next Saturday.
Great, thanks so much, Abdullah. And could you share, is the first quiz ready to do for everyone? Should everyone have some more information next week? What are the next steps?
Oh, sorry. Yes. So the quiz will be, I just have to make a few small adjustments and we up to, today. Okay.
Great. Okay, so from tomorrow, quiz 6.1 will be ready to do. Thanks so much, Abdullah. And we will see you again next week. I will stay on for 50 minutes to discuss global quantum projects. I also want to respect everyone's Saturday, so if you want to leave or need to leave, feel free to do so. Right at this moment, I see Feroz is re-entering the Zoom. Great moment, Feroz, because we are just going to discuss the global quantum projects, of which where you are really a role model for everyone. And we'll discuss further questions in general about the program.